Now, what about the invertibility of an LTI system? So, what is invertibility? Invertibility means that there exists an inverse for a system, meaning if you have a system, let's say S1, and there is another system S2, if S2 is the inverse of S1, then whatever you feed in as the input to x of t can be obtained at the output of the system S2 when you connect them in series. So, in other words, if S1 was an LTI system with impulse response H1 and let's say it is invertible, then you connect it to another system S2 whose impulse response is H2, and we say that this is an inverse of S1, the output has to be x of t. So, if you see here what is happening, you are saying x of t convolved with H1 of t convolved with H2 of t is equal to x of t itself. In other words, this portion which is equal to y of t convolved with x of t is equal to x of t for all possible values of x of t. This is true only if y of t is equal to the Dirac delta signal. This we already saw as the property of the convolution. So, it means that an LTI system is invertible only if there exists an inverse for its impulse response such that when you convolve the impulse response with its inverse, which is also another signal, you should get a Dirac delta signal. So, if you can find such an impulse response, then you can claim the signal is invertible. Later, when we study Fourier transforms, we will see even a simpler version of how to identify if a system is invertible or not. For now, you have to come up with some kind of signal such that when you multiply h of t with h inverse of t, that signal that you are looking for, and if they turn out to be an impulse or a Dirac delta, you can claim that it is invertible. So, it is not very clear how to find this h inverse. So, given some arbitrary h of t, how to find h inverse? Does it even exist? If it exists, how to find out is not directly clear from this convolution integral. We would be able to easily answer them when we talk about Fourier transforms. But if somebody gives you an impulse response h of t and asks if it has an inverse, it's not, we have not learnt the tool yet to identify its inverse. Okay, but now at least we have learnt that if there exists an inverse, when you convolve that h of t with that inverse, you are supposed to get an Dirac delta signal. In this particular context, one thing that we have assumed is that the inverse of an LTI system is also an LTI system. So, it is true. It so happens that the inverse of an LTI system is indeed an LTI system. So, we can prove that. Okay, let us see why is the inverse of an LTI system is also an LTI system. So, let us say the inverse of an LTI system exists, that is, it is an invertible LTI system. Then the output of the original system is given by x of t convolved with h1 of t, and by the property of linearity we can say that when you feed in an input which is a times x1 of t plus b times x2 of t, the output is going to be a times x1 of t convolved with h1 of t plus b times x2 of t convolved with h1 of t. This is directly following from distributive property and the linearity of our LTI system. Now, let us say S2 is our inverse. So, now when you feed in when you feed in a of x1 of t convolved with h1 of t plus b of x2 of t convolved with h2 of t, because this is an inverse, it is supposed to produce whatever was the input. And what was the input? The input was ax1 of t plus bx2 of t. But remember that if we feed in simply x1 of t convolved with h1 of t to this system S2, what would have been the output? Because it is the inverse, the output should have been x1 of t itself, right? Which means you can rewrite this entire expression here as a times S2 of x1 of t convolved with h1 of t plus b times S2 of x2 of t convolved with h1 of t. So as you can see here, what have we showed? We have showed that there exists an arbitrary system S2 whose input, let us call this as some z1 of t and this as some z2 of t. Now clearly this tells us that the system S2 satisfies the superposition property. So basically we have two signals Z1 and Z2. We have scaled them by arbitrary constants A and B and fed them as the input to the system S2, and the output so turns out to be the sum of the scaled individual outputs, which is exactly the superposition property that was required to be satisfied for linearity. So this system S2 is linear. Okay, S2 is linear, that is good. Now, is it time invariant? That's a question that we have to now ask next. Let's try to find out. So, what is time invariance? So, if there was an input Z1 for which the output was, let's say, x1 of t, then when you time shift the input, the output should also time shift accordingly, right? If this is true, then the system is time invariant. This is actually true here. Why is that true? Because z1 of t minus tau is in fact equal to z1 of tau convolved with the Dirac delta function, which is time shifted. But then once again, you can rewrite this as x1 of tau convolved with h1 of tau convolved with this Dirac delta function. Now once again, we use the associativity and the commutativity, which means you convolve delta with x1 first, okay, which gives you x1 of t minus tau convolved with h1 of tau. So this is z1 of t minus tau, okay. So z1 of t minus tau, which is the time shifted version of z1, is the output of S1 when x1 of t minus tau was fed as the input. If this was the input to S1 and you feed the output of that to S2, it was supposed to produce exactly what was the input, which means S2 would produce x1 of t minus capital T. That's what we have here. So the inverse of an LTI system is also an LTI system, okay, which follows from whatever we just saw. So this tells us how to find the invertibility of the system just by looking at its impulse response if it is an LTI system. Now what about the final property, which is stability? Now what does stability mean? That you give an input which is bounded in amplitude or bounded in magnitude to a system. If the output also turns out to be bounded in magnitude, then you say that the system is stable. So you feed in a signal which is bounded. So if you are giving a signal input to a circuit which is, let's say, restricted between plus and minus 5 volts, you should not expect the output to arbitrarily shoot up to some 100 volts or 1000 volts. You are expecting the output to be bounded between some value, right? So only then it will be a stable system. If you arbitrarily get some high voltage and high current, the system is unstable and there will be some kind of accidents. That's what you want to avoid. How do you check if the circuit that you have designed is stable or not? If it is an LTI system, it is very easy to check that. How is that? So remember, for an LTI system, the output is simply nothing but x of t convolved with the impulse response. In other words, what you do is just simple convolution t minus tau d tau. Now, we are saying that the input is bounded, which means the x is between, let us say, some minus b and plus b. It is not going to be beyond minus b and plus b. And what we want to ensure is that the output, that is mod of y of t, is also less than some finite value. So, the output should be finite. That is what we are trying to say. In other words, we are trying to find out if we can say that this integral, the convolution integral, is less than infinity. That is what we are trying to say. Okay, we will take the absolute value inside and say that this is okay. So, we simplify this, we will say that because the maximum value here is b, so mod of minus b is equal to b. So, the maximum value here is b, we will say that this is okay. So, if this integral is finite, that is the maximum value that this integral takes is, let us say, only some finite number. It can be 1, 2.1, or it can be even 1 billion, but still it has to be finite. So, as long as this is finite, then the output will also have a finite magnitude. So, that is what we are saying, that is the area under the magnitude of the impulse response. So, here we have found out h of t minus tau, and this is true for any t, right. So, you can just simply say that the area under the impulse response, the absolute value of the impulse response, should be finite. In other words, the impulse response should be absolutely integrable if we want a stable system. So, what does this mean? So, remember, how do we find out the output? So, we just simply take the impulse response, time reverse it, multiply with the input signal, find out the area of the product. Now, what if the impulse response has an area which is already infinite and you are multiplying that with an input? So, for a simple input as a constant, let us say my input is a constant which is always 1. Okay. If the input is a constant which is always 1 and the area under the impulse response is infinity, then what is happening? So, your input is just a constant which is 1, and let us say your impulse response looks something like this, which has infinite area. Then no matter where you move this, you will always have infinite area, right. So, at whatever time instance you compute the output, the infinite area of the impulse response will end up producing an output which is also infinite, because the output at every point is the area of the product of the input and the impulse response. So, if the impulse response itself has infinite area, then you are very likely to get an output which is also infinite even though your input is finite. So, one way to ensure that your system is stable is by ensuring that your impulse response has an area which is finite, and this area should be the area under the absolute value of the impulse response. Okay. So, this notion is what we refer to as the absolute integrability of the impulse response. Now, what if the impulse response was a periodic signal? Then remember, we said that the periodic signal extends from minus infinity to plus infinity. And what would be the area of the periodic signal in one period? It will be some non-zero value. So, let us say, for example, you take the sinusoid. Okay. It extends from minus infinity to plus infinity. Now, let us find the area of this signal in one interval. Okay. So, we take the interval, one interval. If you directly compute the area, it is 0, but you are supposed to compute the area of the absolute value of the signal. So, the absolute value here is computed by computing the area under this portion, right. So, this is some non-zero value. Let us say the area is some capital A. It can be 1, 2, 3 something. It is finite, okay. But then what is the area under the entire signal from minus infinity to plus infinity? It is A times how many ever cycles are present. But how many cycles are present? There are infinitely many cycles, right. So, the area under a periodic signal is always infinity when you compute the area through the absolute value, which means if the impulse response of an LTI system is periodic, then the system is always going to be unstable because it has an area of infinity for its absolute value of the impulse response, because the area of the absolute value of the impulse response is infinite.